Okay, yeah, thank you. This talk will be in English. If you haven't noticed, I have a serious accent. So if we want to make it to the end of the night, we'll stay in English. Today I'll be talking to you guys about, we'll continue the discussion, of course, on memory, but specifically that focus when we move to agentic workflows, that our main limitation, now that we're using that multi-turn system, it is the memory limitation. So let's talk about it. We'll go into context decay as well as engineering agent memory. Okay, that wasn't the button. This one? זה כאילו בעברית. Okay, it's backwards. Okay, a bit about me. I'm a data scientist at WIX. I'm currently working on a user-facing multi-agent system. We're dealing with lots of problems such as working with our infrastructure as well as building automations for users, implementing user customizations, implementing tasks, things like that. As well, I've been in the field of data science, specifically focused in LLMs and generative AI for the past 3 years. And I have a background academically in neuroscience as well as data science. So today, we will start with a quick refresher on the agent. I'm pretty sure you're all up to date, but we'll do it anyway. We'll go into a bit of short-term versus long-term memory. So some context decay, the phenomenon that we are witnessing regardless of the size of the model. And some optimizations. What are some strategies we can use to kind of work with this infrastructure that we're stuck with? All right, this is a refresher of the agent. How is it different from our typical call and response when we talk to a chatbot that's just an LLM? The agent is having still the LLM as its brain, but it has a configuration of tools, a system prompt, and its memory. So when we give it a task or an intent, it's still able to actually go through several decision cycles and cycle through multiple tools like APIs, MCPs, having its system prompt and the memory that it's given to actually come back saying, yeah, like I executed this task. Maybe it took 10 minutes, but it's capable of doing so. Now we'll dive into the brain, the LLM. Under the hood, we're looking at a neural network that was trained on a massive amount of textual data with the architecture of a transformer. Transformer has those main 4 components we're all aware of. We tokenize, embedding, feed it to the attention block and feed-forward neural network, and that outputs all possible tokens that could be output at that stage, and the most likely token is chosen. Additionally, this is a token-by-token loop. If we needed to just generate once upon a time, that would take 3 passes through this architecture. The reason it became so famous in 2016 is from that paper, Attention is All You Need, and that's what we're going to focus on. The attention. Why is it so special? Why is it giving this model such a leverage across the previous ones of handling language? Specifically because it moves past the generic embeddings and taking those multidimensional vectors and able to shift them based on their surrounding tokens. So especially in English, we have a lot of words that are the same but mean differently depending on how they're used. So we now, with the attention, we're able to shift them to what they actually mean based on their surrounding. I'll show a quick example of shutting this sentence to Bert and pulling the attention weights. Bert is just a small transformer. And if I use the chicken did not cross the street because it was too tired, we can see what the model is paying attention to. We can see that there's an attention spike over the chicken. So with our target word it, the model knows that it needs to also have the features of the chicken. The chicken was too tired to cross versus a similar example, the chicken did not cross the street because it was too wide. We maintain the same target word of it, but we no longer have that spike over the chicken, it's more the street. So we can confirm here that Bert has a bit of common sense, and we can see that even though this is a very small input, no matter what we're inputting to an LLM, it's going to have many attention heads depending on the size and the infrastructure, but this is kind of what's happening. There's also a normalization process, so all of these spikes need to add up to 1. We're starting with short-term memory. Quick review, it's the active context within the session. We'll go into long-term memory as well. But one of the problems we're dealing with in short-term memory is the context decay or the loss in the middle phenomenon that was presented in a 2023 paper. This was the graph that was in the paper that we're still seeing over and over today. What they did was, back when all of those models were released, there were varying context windows, maybe like 4K tokens, 100K tokens, now we have 2 million. However, they wanted to see, is the model going to perform equally depending where information is in that window? If it has a target piece of information that it's looking for, if it's in the first position, 5th position, 20th, does it matter? As it turns out, yes. And there's several reasons for it. One, as we can see, is those attention. There can be noise within that context, even though it's not big. These samples were done on 6K tokens. We need to consider the signal to noise ratio as well. There's patterns learned in training data, especially us as well. If we're reading a paper, we'll read the abstract and the conclusion. Same with models, they realize a lot of important information is there. So it's something to keep in mind. We have a lot of metrics that are maybe needle in a haystack that the newer models are kind of optimized to do really well on. However, other than the needle in a haystack, when we need multiple needles in a haystack, we get this U-shape again. So it's not solved. Don't be fooled. So we're going to optimizations. How can we make this U-shape a little bit shallower and kind of maintain that accuracy along our context windows? So by divide and conquer, I kind of mean the strategy of agent orchestration. So if I would have a task that required several steps, in this dummy example, I'm looking to search some technical docs, go to our user database, and implement changes, maybe execute a couple APIs. I could have a frontier model handle several reasoning steps. It would be fine. But when it comes to maybe going past an MCP, not MCP, a minimal MVP, I would want to consider an optimization. Can I break this down into maybe parallel tasks, sub-agents? Can I offload any logic that can be code? So in this case, the get consent, it could be a client-side tool. This maybe wouldn't require an LLM. If I could search multiple things in parallel, maybe I want to have 2 separate agents do that, as well as at the end, then I have all my agents separate. Why is this interest to me? One, this U-shape can be much shallower because the task is much more targeted and focused. There's less noise in their context. As well, I can get to the next optimization of model selection. If my task becomes granular enough, I maybe don't need to use a 500 bajillion parameter model. I can dumb it down a bit, not only saving time, money, and just allowing the process to be much simpler and more maintainable because I have these pieces that are separate and make more sense. So this is just a quick overview of kind of the right tool for the task. I feel like data scientists were always explaining to clients this when they're like, let's use AI. And you're like, wait, it's the if-then. We don't even need a model. So we must be very familiar with this. But if a lot of people are talking about costs of AI and things like this, it's always worth considering, especially when those smaller models like 30 billion or small language models of 7 or 8 billion are getting better and better. Another optimization, very quickly, would be to offload noise. As we said, it's not only just the size of the context window, but what's in it. If we're dumping in JSONs, data, things that might not be relevant, especially as you guys mentioned with RAG, it's kind of an issue. Processing that data, also dynamic tool availability. For us, if we have users on mobile or desktop, we kind of know that on mobile there's several actions you can't take, and so we have the same assistant, but there's several things toggled off because it's not relevant. Things like that. Yes. And we move to long-term memory. This is what Asaf was talking about mostly. These are stored externally and can span multiple sessions. Can still be part of the context window, but it's out of it for now. One of the main strategies we look at is compaction. As you guys notice, it's an option in Claude Code. It's probably the most common strategy. If you have a session with a user, you might think our main thing that we'd go to is let's summarize that session, store it, and then if the agent needs information on the user, it can go through its summaries. However, there are limitations to this. With summarization comes data loss. That's a given. And so we can either spend an endless amount of time thinking about how we're going to build a summary or accepting a loss, but I wanted to present a quick paper that was presented at the International Conference for Machine Learning that was this week. It's called E-mem, I hope I'm saying it right. And they created kind of a new approach, a master assistant architecture for managing those long-term memory sessions. And I'll explain it to you quickly. Basically, they don't use compaction. It's kind of like a not at runtime. It's a smart compaction in the sense that all of the logs stay as is. If you have a session, the logs stay as they are, all of the data is retained, and that session is assigned to a small language model, around 7 or 8 billion parameters. Then you have maybe 1,000 small language models that are each assigned their chunk. They're a master of that chunk, but they're not on, per se. Then when the master agent is given an intent, a query, based on just cosine similarity, certain assistants are turned on. They're giving a summary of their session, what they're an expert in, that's only relevant to that query, and presenting it to master. So the main agent is getting only relevant information that hasn't lost any of its context. And it's cheap in the sense that their results were, it outperformed the previous state-of-the-art architecture that was GAM, graph for agent memory, and by around 8%, and it reduced token cost by 70% because these small models are super cheap and super fast. So I love when people integrate those mini models. They're like very fun. And the last thing I talked about is something that was already mentioned that we can kind of pile on top is that maintenance layer, the model dreaming. It was quite cute in the sense that as you're keeping logs and summaries or things about your users or clients, there's always going to be contradictions, and that memory can go stale over time. So having an offline process to kind of prune it, maintain it, seems like a good idea. And I think that's everything. Just to wrap up, we went over short and long-term memory and agents, context decay and the architecture behind it, as well as strategy to improve accuracy, speed, and cost in agentic systems. That's it. Thank you. Oh, yeah. You guys have questions?
One question.
Oh, yes.
All right. My name is Leo.
Hello.
Ask me. About the latest article you mentioned. So you suggest that maybe to fine-tune several quen chip models with, let's say, data that should be highly dense and organized.
It actually wasn't fine-tuned.
Taken some kind of a routing model that we go to
The routing wasn't a model. It was just cosine similarity. So based on the query, whatever was, each chunk has keywords assigned to it. Whichever chunk was relevant is on. These models are not fine-tuned. They're as is. And they just analyze their chunk, produce a relevant summary up, and then the main agent is given the relevant summaries at runtime, but it's so fast because of the size of the model that there wasn't any fine-tuning needed. They found the hyperparameters to be around, I believe, 7,000 characters per chunk, or words, 7,000 words per chunk, which is a decent size, like a size of a session.
So each thin model has its own data.
Yes, it's given its own, like it's master of its chunk, and it's like off most of the time.
Do you now invest more in avoiding contamination during compaction or maintenance?
What do you mean?
Just repeat the question.
He asked if you invest more time in avoiding contamination.
In your team, do you invest more time now and effort into avoiding contamination and poisoning in the compaction stage or in the maintenance stage?
I'm not sure I totally understand. I think we're optimizing on all ends. Like, it's multiple engineers and stuff, so everyone's like tackling their, let's do this, let's try this. Like, everything is happening all at once, I would say. I would optimize, yeah, yes.
Yeah, thank you, Boop. Excuse me. Who's orchestrating the split of the division of labor? Like, is the main agent deciding how to chunk?
The main agent, I think, can, in the sense that in the sense of like Claude Code can decide like I have a lot to do, let's like run this in a sub-agent.
Yeah.
But I would prefer maybe it's like more of an AI engineering thing to have control over it, where I know that some process is going to be like heavy token-wise, and I want to do an exploration across an SDK. I want that to be in a sub-agent regardless.
So like in the organization, the AI agent would build a tool, the AI engineer, sorry, would build a tool which this is its purpose, like to flag an assignment which needs to be split into chunks, and then how the chunks...
No, it's more like the engineering behind it. Like if you're building an assistant, you would know that like certain tasks, like let's do this, let's offload most of this context where I have these massive tool JSON schemas and whatever. I don't need that in my main agent's business. I just need to know 200 status worked, something like that.
I'm sorry, maybe I'm not being clear.
Oh.
So like,
Maybe I don't get it.
how technically we actually give the instruction to the agents to use these small models?
Oh, no, it's me who's deciding the model. I guess you can, okay, there is an option of giving an agent saying, like, if I say hi, you have the option to maybe kick in Quen. There are those architectures that exist, but I think either or.
So like you decide per assignment if it should be chunked and
Our architecture, I don't think is per assignment. I didn't check with our guildmaster what we can share. I joined this very late, but both are valid. I think you can decide, like, my system needs to run on this, whereas these separate subsystems, like, we're engineers, we can touch all of the code. So we can have certain models and certain components, but you can also just dynamically change the model, according to the request, or again, have the agent. I think all are valid, and just testing on your use case what works.
Okay, thank you.
Last question. Oh no. Yeah, sure.
Oh, yeah, with the small agents.
So what you do with the SLMs is basically like RAG, but instead of feeding the chunks directly into the context, you're having these SLMs do a summary.
Yeah.
So I guess I'd like to understand at what chunk size is it good to do? Because if it's really small chunks, you don't need the SLMs.
paper,
if it's too
yeah.
big, that it's Maya. Please repeat the question.
Yes. So he asked, like, if you're just doing a reg, the paper that was presented, what's the chunk size? Because that's a question that's popular with reg. Because if the chunks are too granular, what's the point? You have like 7 subagents or more. So whenever the paper asked the same question, it looked like they used 4,000 words as like their chunk size that like worked best across use cases. But it was from, I believe, like, they went up to 8,000 as well. I think it's a hyperparameter that does need to be tuned, but it wasn't so small that I was like, this is just fun for a paper and not for something I could use. Yeah.
Great. Great. Thank you.
Okay.